So the goal of this homework was to generate an image that would be displayed on the screen of a monitor through the VGA cable. Now, after creating the project, we imported the hardware image generator, the top VGA, and the VGA controller files into the project. Then we would go to the VGA controller, and I used this video timing calculator to find the DMT values for setting up a 1920 by 1080p at 60 FPS image. So I used a pixel clock of 148.5, and then all the rest of the values I filled out from the table. And using this, so I put the values that I needed right here in the VGA controller, and then I went to the top and I set up the PLL IP. And what I will show you right here is the configuration of the PLL IP. Now you can see that I set the reference frequency to be 50 megahertz to match the board. I disabled the enable clock output port, and I set the desired frequency to 148.5. It doesn't quite reach that, but it's close enough. And then I generated the IP, and I named it DCM Altera to match the code so that it would just come right in here. So then the next step was to create the SDC file, which is shown right here. And using the IO planner, the pen planner, we set up all of the pins for the input and output ports. And then we generated the SOF file. So I am now going to cut to a video showing the monitor with the output from the board. This video shows what the monitor looks like using the default code, where it generates two squares. In the upper left hand corner you see a blue square, and then in the rest of the screen there's yellow. Now what we also did was we tried to estimate the power consumption, and this was done using this Excel sheet right here. So what you can do is you can go to project and you can generate an early power estimator file. And then once that file has been created, then you can import the CSV file into the software or into the Excel sheet. And with that, you can see you can set the ambient temperature. You can set the toggle rate. You can set the toggle rate. You can see the different logic used throughout the system: RAM, DSP slices, IO, PLLs, clocks, all that stuff. But right here, you can see the static power and the total power used in the FPGA. And what you can also do is you can compare this to the power estimation tool of the built into Quartus Prime. Now if you hit start on that, then it will generate a power analysis report. And you can see in the summary right here the total thermal power dissipated, the core dynamic power, thermal power dissipated, and the core static thermal power dissipated, as well as the I/O power. Now this report is probably going to be a lot better than the estimate given by the Excel sheet, but the other report is a decent approximation without actually building the entire system. Hello, so today I'm going to be going over the EEDG 6370 homework 5 for the fall of 2024 at UTD. Now for the second part of this homework, the goal was to modify the code so that it would display a message on the screen in UTD orange or green. I selected the message to be the I love FPGAs message, and this would be displayed in orange. So how I modified the code was, first I added ports for allowing the clock and reset signals to enter the image generator. I did this to improve the timing and allow a cleaner image to be generated. So after adding the clock and reset signals, I added constants to constrain the area of the message. And then I added constants to constrain the UTD orange color, which I obtained from the UTD website. And then I also added an array that would have stored the message as a pixel art, using ones for orange and zeros for white. And then I added signals that would allow me to traverse the array. Now here you can see that I added a process, and what this process does is it has a row and column counter and a row and column register, and then a column or a color enable. If outside of the bounds of the message, then the color will be set to 0. Color enable would be set to 0. Then within the bounds, it'll count up to 30, and then it'll increment the column it'll increment the column register. And once it reaches 52, then it'll roll back over. And when it rolls back over the column register, it'll increment the row count. And when the row count reaches 4, or when the row count reaches 30, that'll increment the row register. And when the row register reaches 4, then it will roll that back to 0. So what this basically does is it allows for this small array to display a much larger image, where it'll display this pixel for 30 rows, or no, 30 columns, and also for 30 rows. And it'll also display this pixel for 30 columns and 30 rows. And it'll display this pixel for 30 columns and 30 rows, and so on, thus making this a much larger image on the screen. And what you can see right here is that it uses the row register and column register to index that message array. And then right here, what you can see is that when color enable is 1, then red, green, and blue are assigned to their UTD red, green, or UTD orange, red, green, and blue values. And otherwise they're set to 1 for the background, and then if off of the screen, then it'll be set to 0 for black. And now with all these changes, I will show you a video of it working. And this video shows the modified code where I have it say I love FPGAs in UTD orange. And now that you have seen it working, thank you for watching.